Good morning. We are going to recap chapter 3 thus far. Let me make the screen bigger. Here are the topics that we are going to be going through in chapter 3. Continuity is kind of its own little thing. Then we're going to look at a bunch of different functions. We got 3 functions here. We got another 2 here. There's 1. This is a different type of function. And we're also going to look at this relation, which is slightly different than a function in that it doesn't have as many rules it needs to work with. We're going to get through about halfway through here today, those piecewise defined functions. The reason we're exploring all these guys is so that we can start doing things to them. And these are kind of our verbs that we can do to these are nouns. We can dilate, reflect. We can talk about its symmetry, and that will relate to odd and even functions. We're going to bring that in actually today, and we can translate them. Okay, let's jump in and start talking about continuity, or whether or not a function is continuous. A function is continuous if it can be drawn without lifting up your pencil. If there are no gaps, if there are no jumps, doesn't mean that it goes on forever, like the word continuous kind of does imply. It just means that you don't zap from one place to another. There are real continuous functions in the world, such as temperature. You do not go from too hot to too cold without going through just right. When you are in a plane and you're climbing altitudes, you don't suddenly jump from 20,000 feet to 30,000 feet without going through everything in between. Most functions that we have looked at are continuous. There are 2 main enemies to continuity, and that is dividing by 0 or taking the square root of a negative. Now, even if your previous mathematical abilities allows you to take square roots of negatives and end up with imaginary numbers, their graphs really won't show there, and so their graph is going to be discontinuous, and that's what we're talking about. Okay, looking real quickly at this guy, 7x minus 14 over x minus 2. Well, I know I'm not allowed to divide by 0, so x may not equal 2. And what might be shocking is how similar this next one looks, where again, x may not equal 2, because if x is 2, 2 minus 2 is 0, and I end up dividing by 0. But their graphs are dramatically different. And let's explore why. I'm going to have to pause this for half a second. And we're back with Desmos loaded up now. I put that first function into Desmos, and it seems like this very boring straight line where you can't even see that there's something weird happening when x equals 2 until I go and hover over it, and it says, oh, 2 is actually undefined. This is how I would want to draw the graph, with that very large circle kind of showing you that it doesn't exist there. Although in reality, if the computer were to graph it, you would never see it because that point is infinitely small. No matter what number you plug in, it appears you get out 7. If your favorite number happens to be 3, you plug in 3, you get out 7. If your favorite number is 52 or negative 12 or 137 million, you're still going to get out 7. With the one exception, if your favorite number is 2, it just doesn't work. On the other hand, let me see what happens when I change this number ever so slightly from 14 to 13. And holy cow, that doesn't look anything like the previous graph. And we'll still see that there is no value here when x equals 2. In fact, let me plug in the line x equals 2. And we see that that is what's called an asymptote, a line which this graph approaches but never reaches. So now why is that? Let's turn off Desmos and continue going here. Notice that the top of this one is factorable. I could pull out a 7. And when I do so, I get x minus 2 over x minus 2. And those x minus 2's cancel out in almost every case. Thank you to my daughter for lending me her Crayola thing here. Those cancel out in almost every case, except x still may not equal 2. 0 divided by 0 doesn't cancel out. 0 divided by 0 is undefined. So, so that's important. And when it cancels out, I'm left with 7. No such luck over here. Again, if x were ridiculously close to 2, like 2.000001 or 1.9999999, even those would cancel out. 2.000001 minus 2 is the same thing on the top and the bottom, and therefore would cancel out. Over here, if x were ridiculously close to 2, things get a little bit wonky. If x were just a little bit bigger than 2, then when I subtract 2, I'm going to end up with a very small but positive number. And when I divide a normal number by a very small number, I'm going to get a huge number. So things are going to get a little bit weird over there. Likewise, if it were just a little bit less than 2, when I subtract 2, I'll end up with a negative yet very small number. And when I divide by a negative yet very small number, I'll get a very large yet negative number. And that's why I get an asymptote over here, where I just get a hole over here. If I were going to bicycle across this, I couldn't do it for B. And for A, I might feel a little bump when I pass over 2. Just that one infinitely small point is missing. Okay, this is that other branch of stuff which causes discontinuities. And that is it'll be discontinuous when the argument of the square root, what's inside the square root, is less than 0. This one's a little tricky. Let's look at what's in the square root, x squared minus 1, and find out where it is equal to 0. Well, x is going to equal plus or minus 1. Either you could factor this, it is a difference of squares, x plus 1, x minus 1, or you could move the 1 over to the other side, take the square root, and remember your plus or minus as you're taking the square root of a square. So on my number line here, my interesting points are -1 and 1. And we'll see that in between -1 and 1, if I were to try anything, it wouldn't work. It is discontinuous all the way from -1 to 1. I have this big old gap. I could not possibly bicycle across that gulf. If I were to look at the function here, if x were 1, 1 squared is 1, 1 minus 1 is 0, and the square root of 0 is 0. So I'd end up with that point. And then something headed off in this direction. Also over here, I'd end up with something headed off in that direction, but nothing in between. The function is simply undefined between -1 and 1. Okay, so let's take a look now at a bunch of functions. And again, this is not something which I think is going to be new and different and weird or anything like that. We spent a fair amount of time looking at quadratics already. Algebra 1 had more lines than we can shake the stick at. And the cube function is probably something you're pretty familiar with. We're just looking at it through a slightly different lens, not discrediting anything you already know about these things, but just kind of getting them well in mind. So when we start doing things to these functions, it's not so weird. This particular line is the basic line. It is the identity line. Identity in mathematics usually means it doesn't do anything. The identity in addition is 0. Adding 0 doesn't do anything. The identity in multiplication is 1. Multiplying by 1 doesn't do anything. The identity function is the function that doesn't do anything. You plug in a 2, you get out a 2. It didn't do anything. You plug in a 7, you get out a 7. Again, it did not do anything. It is a line. In previous classes, we would have said, oh, it is a line with a slope of 1 and a y-intercept of 0. All of that stuff is still, of course, true. We'll explore it more in a little bit. Let's take a look at the basic most function, y equals x squared. It is, of course, is parabolic. We can talk about it decreasing from negative infinity down to 0 and increasing from 0 to infinity. I often make the half joke, half real question. Is it increasing or decreasing when x equals 0? And the joking answer is no, as in it's not increasing or decreasing. So a little bit of a trick question there. This one has a domain of all real still, but the range is limited to the positive numbers, including 0. The new word, which I'm assuming is new to everyone, is concavity. I play around with the definition of concavity a fair amount. People seem to be okay with what it is, although putting it into very formal words is a little bit hard. This is concave up, and right now I am comfortable with saying if I were to pour water into it, the water would stay if it were facing up. Over here, on the other hand, where we have the cube function, this part is concave up and this part is concave down. Now, admittedly, if I poured water right there, it would flow out. But for the concave up part, it's not going to escape. If I turn it upside down, the concave down part, it wouldn't escape through the concave down part. It has more to do with curves than that, but we will get into it. The change in concavity, which occurs here at 0, 0, makes 0, 0 an inflection point, or change concavity. The domain of this guy is all reals. The range of this guy is all reals. But as mentioned, we get a chance to formally say all that. So the domain in interval notation is from negative infinity to infinity for the identity function. F of x just equals x. The range, exact same thing, from negative infinity to infinity. It would not have been wrong to say that the domain and the range are just all real numbers. My intercepts, both x and y, are the point 0, 0. It has no asymptotes, as none of the ones we will be exploring in the next little bit seem to. It is increasing always. It is always increasing, meaning if I were to bicycle across the page from left to right, I would always be going uphill. There are all kinds of symmetries that we can explore about this. Any line which is perpendicular to it is an axis of symmetry. For example, if I were just to draw in that line and say, oh, if we reflect it that way, it's exactly the same thing. It has, though, more importantly, what we are eventually going to learn as odd symmetry. For odd symmetry, if I take f of x and get y, if I take f of negative x, I must get negative y. So pick your favorite number as long as it's not 0. Not that it wouldn't work if it were 0. But what is f of 7? Oh, it's 7. What is f of negative 7? Oh, it's the opposite of what I got before. It is negative 7. Concavity, this one has none. It has no curve to it. And important points, these are just a couple of points which I personally think are kind of neat. They aren't anything which would hold water if I went to a math conference and said, hey, you know the important points of the identity function? No one would necessarily agree with what they are, but 0, 0 seems like an obvious candidate to me. 1, 1 and negative 1, negative 1 are also good ones. The reason I want to keep an eye on some important points is once we start doing things to these functions, I want to see how some points move. For example, if I were to stretch it one way versus the other way, 0, 0 might stay exactly where it is, but that doesn't mean that the whole shape is exactly where it is. Okay, moving on, we've got properties of the square function. The domain, once again, is all reals or from negative infinity to infinity in interval notation. There is no number which I can't square. Let's move the paper so we can see it. There's no number which I can't square, even if it's difficult to do. There is no number which can't be squared. The range, on the other hand, includes 0. So I have that square bracket there at 0, and it goes up to infinity. As long as it is a positive number or 0, I can get that number out. You want to get 712 out? Great. Plug the square root of 712 in. Or for that matter, negative the square root of 712. My intercepts, plural, are really a singular point. They are, it is, I should say, the point 0, 0, and it has no asymptotes. A big difference here is that I am decreasing on the interval from negative infinity to 0, and I should say decreasing, and I am increasing on the interval from 0 to infinity. Notice that I use these circular brackets, always at infinities, but this time also at 0, implying that at 0, I am neither increasing nor decreasing. This symmetry is considered even symmetry. And what that means is if I plug in a value x and I get out a value y, if I plug in the opposite value, or the additive opposite value, negative x, I'll still get out the exact same thing. For example, if I plug in 7 again, I get 49. If I plug in negative 7, I get positive 49 again. I get the exact same thing. F of x equals f of negative x, if you want to use a little substitution here, or perhaps the transitive property. The concavity of this guy, it is concave up, and that kind of fits with my, it would hold water while facing up. Important points. I think 0, 0 is an obvious choice. It is an intercept, it is the vertex, it is the minimum. But less obvious, I think 1, 1 and negative 1, positive 1 are also good ones. If someone said, no, I think 2, 4 and negative 2, 4 are important points, I would not be able to argue with them. Those are good points as well, just as long as we have a few so we can look at them. Okay, next up is the cubic function. The domain and range, I'm going to write in the fastest way, are all reals. The intercepts, again, are 0, 0. It has no asymptotes. This one is a little bit confusing on the increasing, decreasing for some reason, although it's always increasing. I don't care where you are on this curve. If I draw a little bicycle, I am headed uphill. That is not a good bicycle drawing, but I am headed uphill there. I'm headed kind of uphillish there, uphill there as well. So I am going to call this one always increasing. The symmetry is odd. The concavity changes. It is concave down from negative infinity to 0. And again, concave up from 0 to infinity. Important points seems to have the usual 0, 0, 1, 1, and this time if I plug in a negative 1, I get out a negative 1. And that's kind of implied by that odd behavior there. Okay, this is what we covered in the next day of chapter 3. I think that deserves a good sip of coffee. Related functions, the square root and the cube root function. The square root function, right there, has a limited domain. I think it's the first of those that we have seen. You may not take the square root of a negative, as we discussed in the continuity section. well, and a limited range for that matter. The cube root function does not have a limited domain. You can take this cube root of a negative, you will get a negative, like the cube root of -8 is -2, because -2 cubed is -8. I refer to this guy often as the swimmer dude. To me, it looks like a guy in mid-swimming stroke. And absolute value, kind of a different fish there. I have a couple of bad absolute value jokes. For example, I always say that if the argument, what's inside of the absolute value, is positive, then absolute value does absolutely nothing. I also make the analogy that absolute value is much like a car wash. Regardless of how you come into a car wash, you go out with a clean car, which I consider to be a positive thing. No matter what you put into the absolute value, you come out with a positive number. Presumably stuff that you are familiar with. Okay, let's get through the nitty-gritty of these three. The domain of this includes 0. I am allowed to take the square root of 0. In fact, I'm good at it. It's just 0. My range, therefore, does include 0 and goes up to infinity. My intercepts seem pretty normal here. It doesn't have any asymptotes. It is always increasing, although it is getting less and less steep. It certainly is always going uphill. This one has no symmetry. There is no line I could draw and reflect it over and have the same graph. There is not a whole lot going on there with symmetry. Concavity, it is concave down, as in if I were to flip it upside down, then water would continue to run, but it would never run out. The important points, 0, 0 is definitely a starting point. You can't say it was a starting point for anything else, because those domains included more things on either side. But here you can. It goes through the point 1, 1. And since we had 3 important points everywhere else, let's say it includes the point 4, 2. You want to throw in 9, 3, great. I'm moving right along. We've got the cube root function. Once again, a cube root is really asking the question, what multiplied by itself and multiplied by itself again will give me the number inside? So if I asked what the cube root of 1,000 would be, I'm saying, okay, what times what times what? All the same what, of course, equals 1,000, and my answer would be 10. My domain is all reals. My range is all reals. My intercept seems to be the popular choice, and it has no asymptotes. This guy is always increasing. I'm going to say always right there. It has odd symmetry. Another way of saying that it has odd symmetry is that it is a reflection of itself over the origin, over this point. If I were to say, oh, okay, well, I like this point, and I were to draw a line from the origin to that point, if I drew that exact same line, just double in size, going the other direction, then I would end up with its reflection over there. Those points are just reflections of one another across the origin. From 0 to, from negative infinity to 0, it is concave up, and from 0 to infinity, it is concave down. What is its concavity at 0? Is it concave up or concave down? No. The important points, let's go with -1, -1, 0, 0, and 1, 1. Not that those 3 points alone could define what this shape looks like, those 3 points are linear, and clearly this is not a line. Yet those are good points to follow around once we start doing these things. Last up is this absolute value thing. The domain, I can plug in all reals. The range, very much like a parabola, is from 0 to infinity. It kind of looks like a juvenile attempt at drawing a parabola, which of course is curvy, not straight, but it has a lot of the same characteristics. It has that vertex. It has a minimum point, all of the above. Intercepts 0, 0. I think we're bingo on everyone having that intercept thus far. Asymptotes doesn't have any. Increasing or decreasing? Well, it is decreasing. I'm going downhill from negative infinity to 0, and I am increasing. I'm going uphill from 0 to infinity. Hopefully you get my joke. Am I increasing or decreasing at 0? No. Symmetry, it has even symmetry. If I plug in 7, I get 7. If I plug in negative 7, I get that same positive 7. There is no curve to this, so it does not have concavity. This is where my analogy that whether or not it would hold water really falls apart, but that is okay. Let's go with the normal negative 1, 1, 0, 0, and 1, 1 points. Okay, I'm going to pause, take myself a nice long break here, and we will get back to what I believe should be relatively new, these piecewise defined functions. You know what? I'm just going to make them 2 separate recordings. All right, let me stop that.